pass over to Jeff.
Exactly. Thank you very much. Hi, everyone. Yeah, it's really nice to be here. This is my first time at CERN. It's very exciting to be here. I'm very excited and interested that there is some interest in Julia around here. And Graham told me that there's interest in deploying Julia here in applications where you might use C++ before. I put replace in quotes because you never really replace programming languages, right? We're still using Fortran. So it's what it really is, can you use it for the kinds of things you might have used C++ for? But that's too many words. And so he told me there was interest in this, and I said, oh, that's pretty cool, because there's in many other areas, especially commercially, like at ASML, there's also a lot of interest in this topic. So there's a lot of development activity, especially in my world, going on around this right now. So I will report on some of that. Of course, when we started Julia, as you probably could guess, we were after the MATLAB, Python, and R programmers. That was the target, because those languages are usually kind of slow. So you have an immediate selling point where we can, if you can speed up someone's program 10x, you can get their attention. So that was sort of the original target. But in many ways, I would rather sort of not be selling performance, because performance is, eventually everything is just going to perform the same, right? No matter what you're using, as long as you work on it long enough, it will eventually perform as well as you need it to, and then you're kind of done. So it's sort of not that interesting, but it's very good for selling a language in the early days. So we kind of had to do that. But I would actually rather be selling productivity and other things like that. But it's just a lot more subjective, and it's harder to convince people. But now maybe we might be getting to the point where we can sort of switch modes, and people believe us that Julia is fast. We don't need to convince them of that anymore. And now maybe we can switch to selling the productivity. And fortunately, this the front end versus back end language distinction is not fundamental, right? And especially CERN, I know, is famous for interpreted C++, right? So you can use C++ interpreted and interactively. You can use Julia compiled. And in some ways, we kind of planned for this, because our compiler, even though you can't tell when you're using it from the interactive prompt, does a lot of static analysis, and there is a lot of machinery going on in there that you need to do this kind of thing. It's just kind of not exposed yet, and so we're getting to that point now. All right, so there's some reasons why C++ programmers might like Julia, and we've seen this happen where we get some interest from that group. And one reason is there's a lot of overlap in some of the most popular features of C++, like overloading functions, templates, except without angle brackets, so it's nicer, and the kind of specialization in performance you get from templates, where you can substitute in different types and you get specialized code for that, right? That's one of the top reasons to use C++, and we do that too. So, and of course, good C interop, and it also has the similar kind of multiple levels of abstraction that you can work on. You can work at a pretty high level of abstraction in C++, but you can always drill down to pointers and bits and bytes and things like writing manual vector instructions when you need to. You have the access to all that power when you need it, and in Julia we try to do that as well. So there are lots of things that the languages actually have in common, even though it doesn't look like it at first. And also, depending on the application, there are cases where it is actually a lot easier to replace sort of the back-end language. Because if you have a case where, say, sometimes there's just one developer or a small group of developers that develops a library, and then there are maybe thousands of users of that library. Maybe they use it from Python, for example. It's actually going to be a lot easier to change the implementation language than to change the language that all of the end users are using, right? So in that kind of situation, it can be potentially very easy to replace, say, C++ with Julia, and just say, what, next version of our library is going to be in Julia. And we would like you to be able to do that and have it be totally transparent to the end users. So they don't even know that that's happening necessarily. So yeah, just to quickly show the feature correspondence, overloading, that just maps directly. The overloaded functions just become Julia method signatures, and methods, they're dynamically dispatched. So it's the same feature also does methods. Whenever you have a class in C++, you can just add a method at any time in Julia, and you can do that. Templates, if you have a template parameter T, we have this curly brace syntax instead, and you can get the same expressiveness, just with, I would argue, slightly better syntax. But so you've got that, and then template specialization, very important. We can do that just by method specificity. So you can just write a definition that has, the type you care about specialized in there, and you can overload, that case. So all of these kinds of things that C++ programmers love, they see that you can do this in Julia, and they think, oh, maybe I could use this language. So, but can I deploy it, right? You can't do everything just typing at the prompt. Sometimes you have to deploy something. I need an executable to send to someone, or a shared library to send to someone. And then, of course, there is the checking. So in Julia, we don't, culturally, we don't really love compile time checks that much. I want the language to let me do whatever I want and see how it goes, and kind of only give an error if something kind of really goes wrong. Don't prevent me from doing it in the first place. Let it run as long as it can and see what actually goes wrong, which is great for experimenting. It's great for prototyping. It's great for things that sort of break people's typical object models. Like you might have, so like something like units, for example. People defined a units package in Julia where they don't follow the same algebra as normal numbers, right? Because they're not closed under multiplication, for example. So if we had some kind of system that checked that, oh no, x times y has to give the same thing, so that's not allowed. That wouldn't work, because then you couldn't implement units. And there are lots of examples like that, like symbolics.jl, which implements a whole symbolic computing thing. You couldn't do any of that if we had very, very strict rules that prevented you from even trying to define these things. So instead, we let you define them and try to run with them. And then sometimes things just break, in the middle of your day, which is not great either. That's not necessarily what you want, but at least it'll let you try. And so, this is something we're working on now. Is you want to at least have the option to say, will you please check this for me, and let me know what might go wrong before I've been running for 5 hours and I find out later that something went wrong. So that we're bringing this online now, because actually, as I said, the compiler internally actually has a lot of that information. It's just not telling you. So it's when you run stuff in Julia, very often we have already gone in there and we have proven that some error is going to happen, or we just didn't tell you about it. Isn't that horrible? But that is where we are now. But we can fix that. If you ask, we will tell you about it. So all right, so here's some, just to go through my items on building binaries. So this is the overview slide from the talk that Gabriel Beraldi and I gave at JuliaCon a couple of months ago. And so this is this new feature that actually just got merged onto master, where it's a big change, but the only thing that really we added was this -- trim command line option. That's it. A lot of code just for that one little thing, and that will let you build binaries where everything that we can prove is not reached is removed from it. So this is then that's really the only difference. But this makes a huge difference in the deployability of Julia, because now when you build a binary, it can actually be a reasonable size instead of including the total union of all libraries and code that you have loaded. So instead of being typically hundreds of megabytes, now it will just be a few hundred kilobytes, maybe a couple megabytes. So that sort of solves that problem. And if you saw Evangelos's talk earlier today, he spared me showing the details of all of this. He showed how to use it and everything, so I don't need to go into too much detail. And you can also find the video of this JuliaCon talk, and we have a lot more detail on this. But the size thing is sort of solved for now. At least there is a solution in place now, and this should be released in Julia 1.12. And now, just as another kind of brief aside, as far in the static checking category, I'll just share very quickly this document that's a draft work in progress. Work in progress draft proposal to have checked interfaces in Julia, so you can say things like, these are the methods you need to define for something to be indexable or to have the has length trait, and you can define these kinds of interfaces, and then we can check them, and then we can also check functions that use them, and so that we can show that, for example, a function that you wrote doesn't have method errors, assuming all of the interfaces of the things it accesses are implemented correctly, and then we can separately check those implementations. So this is a feature that's sort of being designed right now. I wanted to just quickly show this. I can't say much more about this because it doesn't exist yet, but it's in the process of being designed right now, and it's not that difficult really to implement. It's not like a years-long project, so this is going to be something that'll be available pretty soon, I think. So that's coming, and it's been a very common request to have people document and check, have I implemented the right interface? So that's something that's on our radar. Another thing we've been working on is in the static analysis category is this semgrep tool. So this is a tool for finding suspicious patterns in code. It's often used for security audits, making sure code doesn't do things that it's probably not supposed to do. And so the key feature of this tool is it uses a very high level syntax for defining rules. So if in your organization there's like a coding rule that you want to enforce, you can specify the rule fairly quickly using a really high level syntax, and then the tool will check code against that. And so there's a support for Julia that exists in there, and in our platform JuliaHub that our company makes, we have in a nightly build of it. Actually, let's see if I can get to it. Zoom is doing the thing where it's covering my browser tabs with the controls. There we go, yeah. Hide video panel, nope. Okay, no, it doesn't matter. I can just, that's fine. I just go to the, so this is the nightly build of JuliaHub. And this feature exists in here. It doesn't exist outside of this, but it'll be deployed pretty soon. And so I thought it would be fun to look for, let's see, go to packages. And it can run this against open source packages if you want. So I thought it would be fun to look at the JuliaHub packages, of course. So for example, we can go into unroot, maybe. And there's this static analysis tab, maybe a little bigger. So there's a static analysis tab now. And it will show you all of these reports of possible issues it found of various severities. And we have something like 100 of these rules. Some of them are related to CWEs. This thing is, I found it's very, very picky, but it tells you this is the kind of tool people need sometimes for production software. So yeah, try to avoid global variables. Functions should explicitly return a value. It's very opinionated. I don't even know if I agree with that one. Detect the use of user input to construct a file path. Oh boy, okay, yeah, you might want to look into that one. So it'll give you these kinds of typically like security related kinds of reports is what this tends to be used for. All right, so this is another tool that is coming online now. And oh yeah, okay, I put in a screenshot here of some of it in case that didn't work, but it did work, so that's good.
Asked for that to become part of CI. So as a pull request, we only see.
Yes, yeah. So there's a semgrep command line tool. So you can get the command line tool and put in the rules you want, and you could run that in CI. Yeah, you could. Yeah. All right, and now I just want to show some kind of fun compiler static analysis stuff. This is sort of just for fun. It's not a thing you really need to know about. I just think it's cool, which is why I'm showing it. This is not something you ever really need to use. But I just kind of want to show it off because this is one of my fun new toys in the Julia compiler that you may not know about. So we have this thing called infer effects. So as you might know, optimizing and analyzing programs is largely based on various kinds of function theories. So like a theory of functional equivalence, and theory of pure functions, right? So that's where you get the intuitive program transformations, like if I call a function but I don't use the result, well then I don't need to actually call the function. Or if I call a function twice with the same argument, I don't need to actually call it twice. I can just use the result from from the first call, and et cetera, et cetera. But you can't do that if the function prints something, right? If the function prints something, then you can't do that. You have to keep it. So this is the domain of what we call effect analysis, where you have to sort of understand what the function does beyond just computing something, so you know what transformations of it are valid. And this is actually a surprisingly complex and rich area, because the classic example is printing something. Of course, that one's pretty obvious, but it gets pretty interesting because, for example, exceptions is another one. So throwing an exception itself is not really, it's not necessarily make a function impure, right? If some exception gets thrown while computing something, it's not really the same necessarily as printing something. That might still be a pure function at the end of the day. And also it has sort of different properties. Like if in the case of the, say, calling a function twice with the same argument, and that function might throw an exception, just calling it the first time is enough, because if that throws the exception, then that's enough. That'll give me all the exception I need. I don't need to call it the second time. But I can't do that if the function prints, right? So it very quickly actually gets pretty complicated. And it turns out there's different kinds of effects. So if I start with a nice, well-behaved function, let's try plus of 2 ints, for example, I get all green. So what is there? I think there's 9 of them. So there are 9 effects that our compiler knows about, if you can believe it. And you can see if we dump that, it'll show you what we have there. So in the documentation, there's a description of what all of these mean. So they're all different kinds of effects. One of them you notice is the really fun one in the middle there is terminates. We will try to prove termination, and we'll keep track of whether we've proven that something terminates. Always fun, if you're doing problems that are decidable, what are you even doing? It's not fun unless it's completely undecidable. So yeah, so there's all of these effects you can see we have, and if I keep trying other functions, we'll see some interesting stuff. So, right, okay, so print, of course, if I print a string, that's completely red. So that's as bad as you can be. That's just print, can't do anything with that, right? And I don't know if it actually needs to have all of these, but of course it's conservative. If we don't know what it might do, we have to make a conservative assumption. So this one, for now at least, print has all of these. It's really, really bad. And then of course, they're the ones that are in between, like sign, for example. So that's pretty good, except it has this N one, which is, you can see the third one is no throw. And it doesn't have that because sign actually might throw an exception because there are invalid possible argument values to it. So it will throw an exception for invalid arguments. So you have, yeah, so there's a possibility it will throw an exception. So we have to know that. So, or another fun one is like sum. Sum of vector of float 64 is a fun one. That's all over the place. So this one, of course, the vector is difficult because it's a mutable type. So the problem here is, even if I call it twice on the exact same vector, it might not give the same result because the vector might have changed. So that's captured there in this first this first effect about whether it's so-called consistent. And then it thinks, I think there's probably some bounds checks in there. So it thinks it might throw an error, I guess, which may not be necessary, but I guess that's where we are today. And then there are these various other effects about what kind of memory it accesses and all these sorts of really, really elaborate things. But I was getting into this because just this machinery is being developed. It's getting pretty sophisticated. And I noticed that we are now able to do a pretty cool optimization. So the sum function is actually pretty complicated, for better or worse. So you can see, if you do code typed, you can see like sort of what our compiler sees. And basically it's pretty complicated because it's based on a higher order function that uses this map reduce, where it maps the identity function and reduces with an adding function. So it uses a higher order function. It's a little bit elaborate. It's not just like a loop that calls plus or something. So it's quite a fancy function. You can see, okay, yeah, here's a case that returns 0. That must be some kind of empty case, right? All right. And yeah, it's pretty elaborate. Not at all trivial. But I noticed if we do now sum of 1, 2, 3, and again, the reason this is difficult is this vector is actually mutable. I think if we were doing this again, we might make these kinds of vectors immutable by default. I was kind of scared to do that because I thought people would not be really familiar with too much immutable data types, and people would be, be more used to being able to modify arrays that they had. So it's mutable by default, but that makes it very difficult to optimize. Because if you think that something else can maybe see this vector, maybe someone else is going to be changing it at any given time, and that makes it much harder to optimize code, of course. But I noticed, so of course that returns 6. If we look at the code, LLVM code for this now, it ends with return 6. So we are actually able to optimize this to just 6, even with all that machinery of all those higher order functions and everything. Mutable array, all of that, we can reduce it down to just 6. The only embarrassing thing about this is that we actually have a dead allocation in here. There's still a call to allocate. It allocates a vector, initializes it, and then just never uses it. So this I think is just very temporary. I think this will be fixed very soon, but it's I don't know why it's in there, but I think it'll be easy to fix. But so this is new in 1.12 that we're actually able to optimize this, which is pretty amazing. And so this is the developing strength of our static analysis stuff. All right, yet another package that we developed is called allocheck.jl. So this was motivated by people who want to do real-time controls where they don't want to have garbage collector pauses. So the best way to do that is just to write your code so that there are no allocations. And then what you want to do is statically prove that there won't be any allocations. So this package will do that for you. So you can just use allocheck, and it actually has a macro that you can put on a function that says, I want to make sure there are no allocations during this, or you can call it interactively to see what its results give. So for example, if I do sum of a matrix of floats, okay, yes, there are no allocations found in there. But if I do matrix multiply, that's going to allocate a new matrix for the result. So indeed, it finds that there is an allocation in there. So it'll give you an error about that. It'll show you where the allocation is. So you can fix that somehow in your program. So this is a great example of kind of an application-specific sort of static analysis of the kind we like, where we will, if you pass this, and it might be a little bit hard to modify your program to make it pass, but if it passes, you know we've proven there are no allocations at runtime. So that's pretty cool. And another similar tool, so we have, there's a package called jet.jl, whose purpose is basically to surface analysis information from the compiler and kind of show it to you, and you can ask it things. But it's a little bit of an advanced tool. It's a little bit hard to use. So we've been working on kind of a super easy wrapper script for it. So here, for example, I ran it on the REPL because since the REPL is sort of an interactive front end, there's probably going to be some dodgy, sloppy code in there because, it's just kind of a user interface, doesn't really matter. So it's probably, I figured there'd be some dodgy stuff in there. And indeed there is. So this will find your things that would be a typical, C++ compile time error kind of thing, like no method found here, possible access to an undefined variable. And this one is good because it can generally avoid false positives because this is fully data flow analysis based. So it actually knows about all of the types. It will do a deep data flow analysis, and it has a pretty good idea of what is actually happening. So it can avoid false positives most of the time. I think there are actually, so some of these I looked through these, and some of these are actually real issues. There are a couple of methods in there that are just not right. And but yeah, so a couple of them are real issues. But the thing about it is when you run it, it checks every single method in the package, and so it'll get false positives if there are methods that are never entered, because when it analyzes a method, it assumes that something calls that method. But if nothing ever calls that method, of course, then there's not a real problem. And I think that's what some of these are. Yeah, so that's why it can kind of still have some kind of false positives. So this is also something that's coming online, and this will be available very soon. So I couldn't resist making this meme, and then I realized I'm not sure Europeans know who this guy is. Do people in Europe know who this guy is? A couple people, but do people know him from the meme? Who knows him just from the meme? Okay, yeah, it doesn't really matter who he is, but he's the wrestling, the WWE wrestling guy. But yeah, I couldn't resist. But all right, that's basically it, and I will take questions.
Great, thanks, Jeff. If you're on Zoom and you want to ask a question, just raise your hand. Room, raise your hand. Easy user, point and click user interface.
Right, so just like a technical question actually. So we established that the sum function is not consistent on when it's operating on a vector because
it's mutable. Yep.
Right, but then the optimization was shown that for that specific vector, it just builds the number 6 and returns that. How's that optimization done? Because I would assume that that wouldn't be allowed. If we establish that the function is not consistent, then I would assume that we can't evaluate it and just return that result.
Yeah, I think it is depending on a further layer of escape analysis where, so even though it's not consistent, then some later stage knows that in fact, nothing else can reference it. So it actually can't change. So that would be, I think that's the escape analysis doing that.
Was I think an experimental thing, or I guess still is, to declare arrays to be read-only. I know that Will Moses pointed me to this when there was something Enzyme couldn't prove, and he said, try this. Well, that case it didn't help in that case, but is this going to be something less experimental and more official in the future?
I do think so, yeah. I think we will have some kind of immutable array probably in base. Yeah, we definitely need it at this point.
Then we can lock an array after it's done or something.
Yeah, there's some experimental work on that, and yeah, I think that will definitely happen at some point. Yeah,
and also like what you just mentioned, I guess in principle, what sum does, if you go through it deep enough, at some point you can prove that it's consistent, right? Well, just a limit to how deep this thing goes at the moment.
Well, it's not consistent, but the argument doesn't escape. So it's for a different reason. You're still able to optimize it.
Yeah, but I mean, if you look deep enough, there's only get indexes. There's no set index. There's no. So is this because at the moment the analyzer just has to stop at some point because it can't always go all the way through everything, or?
Yes, I think it must be, and it might be partly like a pass ordering issue. Because when you just do, if all I know is that I have a mutable vector and I do a get index of it, that operation is not consistent, right? If I do the get index, that itself is not consistent, right? In the small. But if I later find out that in fact no one else has a reference to that vector, I would then have to go back and say, oh, okay, since this vector doesn't escape, in fact, get index on it is consistent. And then you'd have to kind of repeat that, but we don't do that right now because it's just too inefficient. We're not doing that at the moment.
So for that, doing this read-only marking would really help.
Yes, yeah.
The compiler, whoever has a reference, nobody can change this now.
Yes, it would. And you'll also, if you look through base, you'll also notice that there have been these little annotations popping up like mushrooms of when we know that a certain function has certain properties, but the compiler can't prove it, we will annotate it. As like, we'll annotate it with there's a thing called assume effects. So you can tell the compiler, assume this has certain effects, like assume this doesn't throw an exception, assume this is consistent, and you can actually put that in.
Is this something we should also be starting to do in packages if we are reasonably fairly certain that no matter what types people will throw in, because we have higher level knowledge that unless there's some very weird stuff going on.
You can do that, but just please get it right. Putting an incorrect annotation like that, well, it's sort of like at inbounds, right? Except it's potentially maybe even worse. It's pretty bad to have a wrong annotation like that. Things can go pretty bad. You'll need to have a face shield if you for that one.
Also, another question. You talked about static analysis tools. Does this actually mean that a package also does not need to be initialized to actually perform the checks? Maybe for JET or for the alloc check?
The package needs to be loaded. So that's, so it's semgrep actually works just purely textually. It can work just on a text file, but that limits the depth of analysis it can do. So for the good static analyzers, you have to at least load the package.
Okay, this means when my package has somewhere an error and does not can't be loaded, I can't use the tools to actually find the error, isn't it?
It has to at least load, yes. Yeah.
Okay.
So I think that's a pretty, that's a bar that you can generally meet. I think the only thing that'll prevent it from loading is like just like a parse error or something, which is,
Yes, sure. I mean, it's actually known from other languages that sometimes you can text-based analyze the code without actually compiling and executing the code. This is what I mean.
Oh yeah, it doesn't have to necessarily compile and execute it. It definitely doesn't have to execute it.
Oh, okay, really good.
Yeah, it definitely doesn't have to execute it. That's why it's a static analysis.
Yeah, that's right. Okay.
It will probably do some compiling, and it has to be loaded, but it doesn't have to execute.
Ah, okay, understood. Thank you.
Yeah.
I do have a question myself. This check alloc, this is a static. So if you tell that there is no allocations, then I don't need to run the what I was called the mem profile.
Right. Yeah.
I know that it will never.
You know there won't be any. Yeah.
In that part of the. And if this calls many things, you will analyze the full tree.
Yep. Yeah, it'll go all the way in. And so if it reaches a point where it doesn't know where execution goes, it'll also have to give an error for that because it doesn't know what's going to happen, of course. So it's a pretty strict analysis. It can, but yeah, if you really need that, then it'll do that. Yes.
Any questions on Zoom? Just a reminder, just raise your hand.
I guess now we could start playing around with this JuliaC with the latest nightly, day or so. But this JuliaC JL file, where's that?
It's currently in the contrib directory.
Okay, so it comes with it.
Yeah, it comes with it. I think eventually there's a feature in progress of having package apps, which is basically something that's like a Julia package, but it's for running a top-level command instead of loading and calling from another Julia package, which would be a great feature to have, but it's not fully done yet. So I think eventually it might be one of those. It'll become it'll become an app that gives you a standalone command line tool. I think that's where it's going, but I didn't know where to put it for now. So it's just in the contrib directory.
I also have another question, which maybe is a bit unrelated, but you showed a lot of nice tools which are supposed to be in 1.12. Can you say something about a date where we get a release candidate of that?
So 1.12 is going to, the feature branch for it should be pretty soon because 1.11 is about to come out any day. And so 1.12 feature branch should exist, fairly soon after that. And then that should be finally released within 6 months. We aim for 4 months, but it might be 6 months.
Okay, thank you.
Okay, well, I have one.
Yeah, there is a question.
Go ahead on Zoom. Yeah.
Yes. So you showed this code snippet where you ran the sum of the vector, right? Is this similar to what happens when you use a const expression in C++?
Well, it's just that the compiler was able to do that optimization in that case. So it's, yeah, you don't have to specifically ask for it.
So it does it automatically. So we are moving kind of more computation to compile time that way.
Yeah, but there actually are, yeah, there are ways to move computation to compile time manually if you want to. So if you sometimes people will do that. They'll compute things at load time, say, and then just reference those from a function. Since you can run any expression from the top level in Julia, so you can kind of do that manually if you want to. But this is just the compiler doing its best to optimize things. And yeah, of course, the downside of it is you don't necessarily know when it's going to do that.
Mm-hmm. Okay, interesting. Thank you very much.
Great, thanks for the question, Casper. Yeah, so I have a question as well, which was about the size of the binary, which I think is if you look at the history of binary sizes in Julia, is very impressive. The I think in your JuliaCon talk, you actually go through that.
It's gone down a couple orders of magnitude.
Yeah, it's quite amazing. But I was just wondering about, let's say I start to compile a library in Julia that, I add more and more things to it. I mean, that is still quite a large binary to say hello world.
True.
So, and I think it's fine to have some overhead, but is that overhead expected to be fairly constant no matter, and then I just add my code?
Yes, that's a very good question. And yes, that is basically constant overhead. We pretty much know what it is. In fact, I think it's almost all of that space in hello world is actually due to the double underscore init methods in base and in various libraries, which the problem with those is, of course, the semantics is we promise you that those get called on startup. And we don't know what they might do, so we don't know what might depend on them having run. So we sort of have to run them. And they actually do a surprising amount of horrible stuff, like looking at environment variables and files and who knows what. So they do all kinds of stuff that you probably don't need, but it's very hard for us to prove that you don't need it. So we're going to do something about that. We will get rid of that excess code, but that's a constant overhead. Yes.
Right. Okay, that's great news then. So if I add more and more things to it, then it doesn't.
Yeah. Yeah.
Cool. Anything else? Any other questions for Jeff?
So which kind of features would not be available if we're compiled version of the application? So like I'm assuming like auto differentiation, like would introspection be difficult, or is that no problem?
So it's so you're not going to be able to introspect like the IR because we will delete the IR. So we try to keep all the basic language features like garbage collector, exceptions, all the basic features, and even like tasks, threads. It's all there. So all the language features are still there, but some data might have been deleted. So if you typically do like reflection kind of stuff, like if you if you look for a particular name of an identifier, or you ask for the IR for some function, it just won't be there. So that kind of stuff won't necessarily work.
Since you probably have a pretty good overview of the sort of thing, what would you expect? What that means for like ecosystem? How many of the packages would you compile program? I assume by using a program, it would limit whether your program can be compiled. Dependency is not compilable. Like, is the average? Would this not be an issue for the average?
It varies widely. So there's some in some cases you will have to arrange to do things basically at compile time. Like actually loop vectorization is an interesting example because it does some very clever stuff to when in its init method, when it starts up, it looks at your architecture and actually generates a bunch of method definitions based on what architecture you're running on, which is a very, very clever way to do that. But that's not going to work if you want everything fully statically compiled. So that's going to need someone's going to have to pay some kind of attention to that to get that working in this for a trimmed binary. Because that isn't going to work. And then some very, very dynamic packages like maybe data frames that use vectors of any for everything, you're not going to really be able to trim very much. So that kind of thing is not going to work very well. So yeah, not everything is going to work, but then you'll get compile time errors due to that stuff.
Thank you very much.
Okay, anything else? Once, going twice. Sold to the man in the blue hat. Okay, great. Thank you so much, Jeff.
Thank you.